All right, welcome back. This is going to be 6.6, the fundamental theorem of calculus, which sounds really pretty heavy, but we've already kind of experienced with what's going on in this fundamental theorem of calculus. So let's have a look and see how this goes. Let's add this in, and let's call this 6.6, and here we go. So what this says, so there's a few things going on in here. It says f of x is a continuous function on the interval from a to b. So a is to the left and b is to the right, and this function is defined and it's continuous through that whole thing. Then what we say is we call this the integral of f of x from a to b. So when we have this tiny little a down here at the bottom of our integral sign, and this b up here at the top of our integral sign, this is telling us that we're taking the integral from a to b, a on the left, b on the right. Now, what this says that it's equal to is this next step with the sigma notation in here. This was Riemann sums, where it just adds up all of these infinitely many thin polynomials that all sum up this area. Regardless, what this ends up saying in this next line is it ends up being equal to f of b, capital F of b, minus capital F at a. So it's telling us that if we take the antiderivative, evaluate that at b, take the antiderivative, evaluate that at a, and we subtract those values, the difference between those values will give us this sum. And we kind of saw that at the end of that last section. But here is this as a definition. It is called our definite integral because it's on a defined interval from a to b, instead of an indefinite integral, which always ended up with your plus c on the end because we didn't have our limits to integration. We didn't have a lower and upper bound to this. Okay, so another part of this notation is it's calling it a of x, where so a of x is this integral of f of x from a to b, f of b minus f of a. So really that ends up being kind of the guts of what we're doing here in integration, is we're finding your antiderivative and evaluating it at these two endpoints of our interval. What this is essentially saying is that a derivative and an integration are reverse processes of it. They are the derivative of a function. If we integrate that, we get back to our regular function. That's essentially what this is saying. This is a definite integral because the answer is an element of the real numbers. And then just a few different notes about this. It is defined even when the function is not greater than 0. So this will work for a function like this. If here's a here, here's b over here, we end up with this area, and we end up with this area. The area below is going to end up being a negative area, and so if we just add it all together, it could cancel some of it out, so we have to be careful about that integration, but it is defined even when it is below. The next bullet, A and B, are limits of integration. We have lower and upper limits. Our f of x is called an integrand, and it just ends up being, it's kind of like when we had radicals, and the part under the radical sign is called the radicand. It's the piece that we're integrating. It is the integrand. As mentioned before, the integral symbol with dx, that is one single symbol. We can't really write our integration symbol, this curly s thing. We can't really write that without without saying what variable we are integrating over, that's what that piece is. It is a single symbol. None of the pieces can be taken away. And the process of calculating an integral is called integration. A few properties of this. This is saying that the integral from a to b of f of x is equal to the negative of the integral from b to a. So that's telling us that if we swap around the endpoints, the start and the end of this integration, and if we instead integrate from b to a, we'll get a negative number of that. Property number two is saying the integral from a to a is equal to 0, which makes sense. It's just telling us essentially that the area of this area that has a width of 0 essentially is equal to 0, and that is why. Part number 3 tells us that if we have a constant function, if we have a constant k within here, we can factor that out. We can take that out of the integration and then multiply once we've finished integrating. Number 4 tells us the integral from a to b is equal to the integral from a to c plus the integral from c to b. That comes in handy when we're going to look at something like this. And if here's a and if here is b, if we just went ahead and added all of this together, the positive and the negative amounts would end up adding to 0 or not giving us the full area part. So often what we will be doing is we'll break it apart into pieces and find our integral from a to c, and then we would end up subtracting. We would flip around and go from subtract this negative area from c to b. And we'll get into that as we get further. And then the last piece is just, well, if we have the integration of the sum of two functions, well, we can break that into the sum of two integrations and deal with it that way, and just simplify our process a little bit. All right, so what does all of that mean? It starts off with the area under, determine the area under f of x is equal to 2x squared plus 3 from 1 to 4, bounded by the x-axis. So we can call this A4 is equal to the area that goes from 1 to 4 of 2x squared plus 3. We can't forget our dx, so I'm just going to put that in brackets. This will end up being equal to f at 4 minus f at 1. Right. So what does this look like? This ends up being, our antiderivative to this is, we have the 2 out in front, add 1 to the exponent and divide by that. We have 3x is our f of x. So therefore, f of x we could put our limits like this. We can write it as a square bracket. Our lower bound 1 at the bottom, put our upper bound of 4 up at the top. And let's take this 2/3 of 4 cubed. 3 times 4. And then we're going to subtract 2/3 times 1 cubed. That's 3 times 1. This ends up being 128 over 3 plus 12 minus 2 over 3 minus 3 ends up being 126 thirds plus 9 is, so plus 27 thirds. We add that together, 153 thirds, which is 51. We saw this result earlier when we did this a different way. But now we're kind of streamlining our process. And we're taking our integration from 1 to 4. We evaluate this integral. We find the antiderivative. We evaluate it at 4. We subtract when we evaluate it at 1. And that's it. Question number 2. Determine the area under f of x going from 1 to e. 1 over e to e, sorry. So this ends up being the integral. Lower bound is 1 over e, the upper bound is e. Function is 1 over x. This ends up being equal to the antiderivative at e minus the antiderivative 1 over e. And what is our antiderivative? If our function is 1 over x, our antiderivative is natural log. So this ends up being ln of e minus ln of 1 over e is equal to 1. Ln of 1 over e is negative 1, so 1 minus negative 1 ends up being 2. Number 3. Okay, so the area under f of x from interval from 0 to pi thirds. So the area from 0 to pi thirds, 0 on the left, pi thirds on the right. So we write them on the bottom and on the top of our integral sign, respectively. And we are integrating cos x dx. So the integral of cos, the antiderivative of cos is just sine. So this ends up being sine thirds minus sine 0. Sine of pi thirds is root 3 over 2. Sine of 0 is 0. And that's it. So it ends up being pretty slick. Yes, there's some complications and some little things that we'll have to watch out for. For A, use the definition of definite integral to evaluate the integral from 0 to 5 of 3x minus x squared. So if we do this, the integral from 0 to 5 of 3x minus x squared dx. So we can use a notation when we take this antiderivative of, the antiderivative ends up being 3x squared over 2 minus x cubed over 3. And we can use our limits, our lower and upper bound of 0 to 5. Sometimes we'll see this with a square bracket on the right side, which is just telling us those are our limits to our limits of integration. We sometimes also see it just kind of with a square, a straight line. We could call it 3x squared over 2 minus x cubed over 3, and then big bar from 0 to 5. Sometimes we'll see it like that also. That just ends up being a sign that, okay, so we've now found our antiderivative. Now let's evaluate it at 5 and at 0 and subtract. So this ends up being 3 times 5 squared halves minus 5 cubed thirds. Subtract 3 times 0 squared over 2 minus 0 cubed over 3. This ends up being 75 halves minus 125 thirds minus 0. I suppose that should be plus 0. To get a common denominator, this ends up being 225 over 6 minus 250 over 6 equals negative 25 sixths, which is a curious answer, isn't it? Let's just come back to that in a second here. It's a curious answer because we're expecting this to be an area. And for this to be negative, perhaps it's a little odd. What we need to do here, though, in part B is it says sketch the graph, labeling all intercepts, shade in the area bound by this parabola, the x-axis and the vertical lines of x equals 0 and x equals 5. Okay, so if I do a sketch of this, y is equal to 3x minus x squared is x bracket 3 minus x, right? So when I sketch this, this ends up being a parabola that has x-intercepts at 0 and at 3. It opens down. And if this is 5 here, and if this is 0 here, then this parabola from 0 to 5, what we found the sum of this area. Now, as mentioned earlier, this area above here will be a positive amount. This area down here will end up being negative. The fact that it's a slightly larger area than the positive one, then we add them together. This is why it's given us this answer of negative 25/6, because we've added a positive number plus slightly larger negative area, and when we add them together, we get negative 25/6. So how do we do this differently? Well, in C it says use antiderivatives to determine the shaded area that is above the x-axis. So if we take what we could call A3, and this is going to be the part from 0 to 3, and to go from 0 to 3, it ends up being 3 halves times 3 squared minus, what do we have here? We had x cubed over 3, so 3 cubed over 3. Is being equal to, and then of course subtract zero, which will end up being 0. When we do this, we get, what is this, 27 over 2 minus 27 over 3. So being 81/6 minus 54/6 is 27/6. Or 9 over 2. So 9 over 2 is the area between 0 to 3. That's above the x-axis. D says, okay, so let's use the antiderivatives to determine the shaded area that's below the x-axis. We can call this A5. Be equal to 3/2 times 5 squared minus 1/3 times 5 cubed. And then we will subtract. So that's the antiderivative at 5. Then we're going to subtract the antiderivative at 3. Ends up being 3/2 times 3 squared minus 1/3 times 3 cubed, which we've actually just already calculated. All of this together ends up being 75/2 minus 125/3. We're going to subtract this part, which we've just calculated up above, which is 9/2. This all ends up being equal to 225 minus 250 over 6 minus, let's call it 27 over 6. This ends up being 52 over 6, 26 over 3, negative, sorry, 26 over 3. So if our upper part has an area of 9/2 and our lower part has an area of negative 26/3, then in E, it's asking us to determine our relationship between our answers from part C and D to our answer of part A. So what we have in part C and part D is if we add these together, if we take A5 and we add A3, if we take negative 26/3 and we add 9/2, then we end up with negative 52 over 6 plus 27 over 6. I add those together, I get negative 25 over 6, which is our answer to part A. But what we want to do is to find our total area under the curve. Is I want to take this amount of A3, subtract A5, because A5 is a negative area. I want to take 9/2 and subtract negative 26/3. Do this, we get a true answer of 79 over 6. So the fact is, when we have a function that has a positive area and has a negative area, at this point in between where it crossed over, we have to break our integration into the two separate pieces. And we will subtract that negative area instead of adding it. So to be careful, there's a difference between evaluating and finding an area. If you're asked to evaluate an integral, you're finding the net area. it might end up being negative. We could be adding both positive and negative values together, and so it'll essentially take the difference between those areas, and it'll just give us our net. If you're asked to evaluate an interval, that's what it is asking for. But if you're being asked to determine the area, then you're finding your total area. If there's any negative areas, we're going to have to subtract them, and we'll have to break our integration up into sub-intervals, is what it comes down to. In general, if a function takes on both positive and negative values, then we can interpret the whole area as the absolute value of f of x integrating from a to b. We're going to call it a1 minus a2. If a1 is your area region below the graph of f and above the x-axis, so a1 is going to look like this. It's below your area, below your graph of f and above the x-axis. A2 is going to be a region that's below the x-axis and above the graph of f. What we will do is we will subtract that A2 because it ends up being a negative amount. So number 5, determine the integral of x cubed from -1 to 2 and interpret the value as a difference of areas. Use a diagram to illustrate. Okay. Well, we know what this looks like. We know that x cubed looks like this. If we're going from -1 to +2, and perhaps it looks a little bit like this. -1 to +2. Let's call this one A1 because it's positive. We'll call this part A2 because it's negative. So the integral from -1 to 0, this will be equal to A2. Integral going from left to right, from -1 to 0, of x cubed dx is equal to x to the 4 over 4, from -1 to 0. So this ends up being 0 to the 4 quarters minus -1 to the 4 over 4 ends up being -1/4. That's the area of A2. A1 ends up being the integral, but now we're going to go from 0 to 2 of x cubed dx. My antiderivative is x to the 4 over 4. Follow that from 0 to 2. So this ends up being 2 to the 4 minus 0 to the 4 is 4. So therefore, my total area ends up being A1. I'm going to subtract A2 because it's a negative amount. And this ends up being 4 minus -1/4. Ends up being 17/4 is our total area. And that is it. Good luck, ladies and gentlemen. Let me know if you have any questions, and we'll see you then.